when we're looking at organisms in the soil, energy comes from the sun. How do you take sunlight energy and convert it into stored energy? You know, if the sun's just beating down on the soil, that's heat. We have to store that biology in some way. And so how did nature figure this one out? So through the process of photosynthesis. And you have to remember that, you know, plants have only been on this planet for the last billion years. Relatively speaking, not long at all. How long have bacteria been present on our planet? How long have fungi been around? When we look at rocks from 4 billion years ago, we find fossilized bacteria. And the very first bacteria that existed on this planet, the first sets of organisms were photosynthetic bacteria. I'm sorry, algae came much later. So when, you know, David Attenborough is talking about the beginning of life on this planet, he's only off by about, you know, 3 billion years. So when we're looking at photosynthetic organisms, evolution has happened over the years. But we started out with photosynthetic bacteria. They began all of this 4 billion years ago. And it is the process of storing sunlight energy in carbon chains. So when we're talking about organic, we're talking about carbon chains. We're not talking about anything that contains carbon. Now, so when you look at biochar, is that organic? It's crystallized carbon chains. It's an inorganic, inert material. It takes life to convert these materials into plant-available forms. It's life that makes the carbon chains, which is the basis of organic, because it's that carbon-carbon bond that is stored sunlight. So first thing that we've got to do is have life to do that. When we're looking at plants, they're going to start building those sugars, because carbon chains, simple carbon chains, are just sugars. How long is your sugar going to be? Well, it depends on what the plant requires and how it's going to build this. But part of that 100% of the energy fixed by the plant, that's going to go down into the root system. If it's a weed only puts 20% of the fixed energy that it's made into that root system. Roots of weeds don't go down very far. But we start looking at brassicas, we start looking at grasses, we start looking at shrubs, we start looking at trees, and those roots go deeper and deeper and deeper. Why is it that we have the attitude that the roots of trees only go down 2 or 3 feet and then go sideways? That is not normal at all. That is not the way Mother Nature grows plants. It's an artifact of the damage that we do to soil that causes the root systems of those plants only to go down a couple feet or just a couple inches and then go out sideways. We've damaged the soil. And when your plant is doing that, only putting its roots down, you're either growing weeds, not going to be too sustainable growing weeds, or we've got a compaction layer. We've done something to compact that soil, and because as water moves through your soil and it hits that compaction layer, water will not move from an area of one density into a different density. So as water moves, hits that compaction zone, water is going to be held up. As water puddles, as water accumulates, you cannot move oxygen through water as fast as you move oxygen through space, and that means that that area is going to go anaerobic. And now we're growing things that will kill your plant instead of helping it. So when people want to talk about, oh, there's no problem with purely bacterial-dominated soil, because if all you've got in your soil, most likely you're dealing with an anaerobic condition. Now we're making compounds that will kill your plant. So how do you rebuild that structure? And so we've got to get this life back into the soil. The only thing that truly builds structure in your soil is life. It's not a chemical interaction that's going to do that. If we're trying to build the airways and the passageways to allow oxygen and water and therefore roots to go as deep as they possibly can, you must build structure. So bacteria in your soil, first step, they make the glues to start binding your sands, your silts, your clays, your organic matter into microaggregates. Without those glues, you're out of luck. So step one in a 12-step program is to build your bacterial community. No bacteria, you're not going any further. So critically important to have these organisms. When you start looking at aerobic bacteria, when aerobic bacteria are growing, they're making these glues, copious amounts of glue. Why do they make those glues? Because they're little tiny organisms, and if water comes moving through that soil, those bacteria are going to get washed away from their food. So think about you at the dining room table. If water is washing you away, what are you going to do? Yeah, you're going to grab onto the table. You're going to do the things to hold you right there where your food is. And bacteria are exactly the same. It's the glues that holds them onto your root system. It's the glue that holds them where that organic matter is. They're going to make these micro aggregates to keep them in that place where their food is. And those glues that they're making, when you take microelectrodes and you start pushing those microelectrodes into those places where we've got bacterial glues, the pH of aerobic bacteria is always alkaline. Always. Aerobic. Ooh, what happens when you go anaerobic? Oh, bad nasty. Now we're dropping our pH down to 4, 3, 2, 1, 0. Blast off. So anaerobic bacteria, bad news. And when we have people out there saying, there's no problem with your compost tea going anaerobic, we're going to make some really toxic things that will kill the bad guys. Right. Do they kill just the bad guys? It's not possible. Haven't we heard this story from the chemical world for the last 100 years? Oh, this only kills the target organism. You know, laugh hysterically when they say that to you. Because it's absolutely not true. There is no way to kill just the bad guys. Any of these toxic, anaerobic, nasty compounds are going to kill way more beneficials than they kill bad. So it's absolutely the wrong mindset to think about, I've got to go out there and I've got to nuke the bad guys. Because when you're nuking the bad guys, you're nuking the good guys too. And if you kill lots of things in your soil, who comes back faster? It's the bad guys. I mean, it's just like gangsters in the city, right? You trash some part of the city, who moves back in? You're the gangsters. So, same thing in your soil. You destroy that beneficial life, and it's really hard to get the beneficial life back in. The bad guys grow really fast. Bad guy bacteria. They're out there, they're growing every 20 minutes, they take over. How long, what's the life cycle on the more beneficial bacteria? What's the life cycle on the beneficial fungi, on the good guy microarthropods and nematodes? We're talking about life cycles that may, for example, with the good guy nematodes, you may not have those good guy nematodes reproducing except for once every 2 years. And they produce only 1 to 2 eggs. So how fast are you going to bring back that beneficial community? It takes a long time. Well, can we jumpstart that? Can we make this move along a little bit faster? And what's that material called that we can put into the soil to inoculate these organisms and get all of this moving faster? Bring those population numbers up so that now they grow and reproduce. That material is called compost. Very good. All together now. Compost! Yes! So we can put back this life. So think about these bacteria. They're the good guy bacteria making glues, alkaline. So if your soil is bacterial dominated, what's the pH of your soil going to be? Alkaline. It's not a consequence of your parent material that controls pH. It's the life growing in that soil. If we've got fungi growing, then fungi don't make copious amounts of glue. In opposition to some of the papers that have been written by the USDA, I'm sorry. Most of the glue in soil is actually made by bacteria, and that was proven, about 30 years ago by people looking in the rhizosphere and saying, where are all these glues coming from? Where is all this material? It's bacterial. So now when we start looking at fungi, they don't produce copious amounts of glue. They make a little bit, tiny bit of glomalin, not enough to worry about. Instead, fungi grow as strands. They are threads. So think about when you take a whole bunch of small packages and tie them together with string. That's what fungi are. They bind things together through the strands that they make. And so they're taking the micro aggregates, they're binding them together into macro aggregates, and now we've got bigger air spaces, bigger passages, bigger pores. We can grow lakes and rivers and streams in our soil as the fungi start to come on and build that structure. You can't grow any plant we care about if you don't have fungi in your soil. So we've got to be out there looking for those fungi. When we look at the fungi, they don't make the glue, so we're not dealing with that pH thing there. What is it that fungi do to control pH around their bodies? They're releasing organic acids. And those organic acids are always aerobic fungi, the filamentous fungi. They produce organic acids that have a pH that is between 5.5 and 7. So if your soil is fungal dominated, aerobic fungal dominated, what's the pH of your soil going to be? It's going to be slightly acidic. So when you think about bacteria and fungi, how important is this balance? Ooh, the balance thing. Yeah, extremely important. How are we going to control what plant's going to grow there? Alter the pH. And we're going to alter the kind of nitrogen that's going to be present as well. And when you think about bacteria and fungi, who's in control of where there's going to be more bacteria or more fungi? Them being released, and of course weeds aren't putting very much out at all. But you start thinking about our vegetables, them being released, and of course weeds aren't putting very much out at all. But you start thinking about our vegetables, 60% of the energy fixed above ground is going to be dumped out, going to move down into the root system. 50% of that 60% is going to be dumped out into the soil in the form of exudates. Exudates. What does that mean? Don't you love scientists? We come up with a whole language that you have no idea what we're talking about. So that you have to come to us and keep paying us for our knowledge. So what is an exudate? Exudates are cakes and cookies. Mostly sugar, a little bit of protein, a little bit of carbohydrate. So if I sent you into your kitchen and I say to you, make me an exudate, quite a bit of sugar, a little bit of protein, a little bit of carbohydrate. What is that recipe? So go into your kitchen. Here's my bowl. What's sugar in your kitchen? Pretty obvious. White sugar, brown sugar, honey, syrup, molasses, all those different kinds of sugars. A little bit more fungal if it's got lots of good brown stuff in there. A little more bacterial if it's white sugar. So, right there we can start controlling balance. Protein, what's protein in your kitchen? Milk. Eggs. So put some of that in there. Okay, what's carbohydrate in your kitchen? Flour. So what is this a recipe for? Different kinds of cakes and cookies. Now, does your plant put out just one kind of cake? One kind of cookie? Absolutely not. Because your plant's putting out the cakes and cookies to feed those bacteria or those fungi that will do the jobs that your plant requires. So what are the jobs that your plant requires? Well, it wants structure so it can get its roots down through the soil and get deep. We want those bacteria, your plant wants those bacteria and fungi to build those air passageways, the hallways, the lakes, the rivers, the streams. So any water moving into your soil is going to be stored, it's going to be kept. And those root systems can grow down to it so you can stop watering in the summertime. We have worked in drought systems, we have worked in deserts, where if we can start building this structure in the soil, we don't have to bring any outside water in, and we can take a stone desert into an oasis with open ponds of water within a year. We collect and accumulate. You better do the swale thing. You better make sure your hydrology is correct. The permaculture information you're getting here is critical. But you better marry it together with an understanding of what this biology is doing for you as well. So building structure in your soil so we can hold water. What's the other thing your plant needs from these organisms in the soil? They have to collect nutrients. So when your plant is putting out those cakes and cookies, they're like little telephone messages going out to the pizza delivery guy. Hey, I need some Hawaiian pizza today because I need that ham nutrient, I need that pineapple, I need the cheese, I need that tomato sauce. Or maybe what the plant needs is a little bit of molybdenum or a little bit of boron. And so it's going to put out the message, the exudate, the cake or cookie, that wakes up those bacteria or those fungi to make the enzymes to solubilize nitrogen, phosphorus, sulfur, magnesium, calcium, sodium, potassium, all the nutrients that your plant requires. So what does your plant require today? What's limiting your plant's growth today? Right now, this second. What's limiting it? Only the plant knows for sure, right? So why do we think that we know better than the plant? Is it nitrogen that's limiting the growth of your plant today? I can probably guarantee you that 50% of your plants don't need nitrogen today. They need something else. Well, what other? You know, is it molybdenum? Is it boron? Is it zinc? Is it chloride? Is it sodium? How do you know? None of you have enough money to figure that one out. And then by the time you send that sample into the laboratory and the data come back 2 weeks later, yeah, right. That was useful. So put the plant back in control of its own life. The plant will put out the exudates, and it will grow those fungi, grow those bacteria to make the enzymes to solubilize phosphorus off your sand, your silt, your clay, your organic matter. Any of your soils limited in phosphorus? Absolutely not. None of the soils on this planet are limited in any nutrient required by a plant. So why are you putting out inorganic fertilizers? Why are we putting out rock phosphate? Why are we putting out what's already in your soil in massive quantities? Why are we doing that? Because they can say, oh, look, I put this rock phosphate out there and see how much my plants grow? Yeah, because you're putting out soluble phosphate. Well, but wait a minute, isn't that what we're doing with inorganic fertilizers? Do we need to be doing that? Because your soil already contains thousands of years worth of phosphorus in order to grow your plants. So why is it when we put a fertilizer out there, we see a plant response? Because what you're missing in your soil are the organisms that do that job of making those nutrients available back to your plant. What you're missing is life. Anytime you see a lack of fertility in your plant, the message that should come back to you is, uh-oh, there's something wrong with the life in my soil. None of your soils lack the nutrients to grow plants. None of them. And I'll show you some data, just a little bit, that will document that for you. So the plant feeds the bacteria and fungi depending on what the plant requires. It puts out the telephone message, hey, pizza delivery guy, pizza, send it to me. So these guys, they're enzymes using the exudates from the plant. They make the enzymes to solubilize the nutrients, but where do those nutrients go? Into the bacteria and fungi. Uh-oh, still plant unavailable. So if all you've got in your soil is bacteria, you're still going to have dead plant. If all you have are bacteria and fungi, I'm sorry, you still have dead plants because they're not going to get the nutrients that they need. Oh, we've retained lots of nutrients in the bacteria and fungi. We've grown lots of bacteria and fungi. And where are those bacteria and fungi growing? Right next to the root. Because the plant is putting out the foods to feed those organisms to get them to solubilize the nutrients. But now those nutrients are tied up, retained in the bacteria and fungi. You're not going to lose any of those nutrients because they're kept in the bacterial and fungal biomass. Are the bacteria and fungi going to be washed away by your water? No. So they're held, they're retained, they're kept there. Now how do we make them plant available? That's where we've got to have our lovely little third trophic level organisms. We got to have protozoa that eat bacteria. The aerobic protozoa, flagellates, and amoebae. As soon as that oxygen starts to go too low, flagellates and amoebae going to go dormant, stop doing their job. And the bad guy protozoa wake up, the ciliates. So start using the presence of flagellates, amoebae versus ciliates to tell you when you are going over the edge into an anaerobic condition and you're going to make some of the most toxic materials known to plants. Nematodes. Fungal feeding nematodes eat fungi. What do bacterial feeding nematodes eat? What color was George Washington's white horse? One of those questions, you know. So bacterial feeding nematodes eat bacteria. And so anytime one of those good guy nematodes eat one of their prey groups, anytime one of the protozoa eat bacteria, or any one time one of the fungal feeding microarthropods eat their prey group, nutrients are going to be released. But it's not just nitrogen. It's going to be phosphorus, sulfur, magnesium, calcium, sodium, potassium, all. How many essential nutrients are there for a plant?
17.
I love this one because we do not agree in the world of science.
1,000.
So when you think about nutrients, how many elements are there in the periodic table? And your plant needs all of them. Right now when you talk, well, think about when I was a child, many years ago, back in the 1950s, how many essential nutrients did plant physiologists, botanists, plant people talk about? 3. NPK is all your plant requires. Yeah, right. How true was that? So by the time I get into high school, how many essential nutrients are there? 18. 18. Okay, today, when we start talking, you know, because think about through time, plant physiologists have been doing experiments, and many, many more experiments have been done to show that these other nutrients will limit the growth of your plants. If they're not there, if they're not available, your plant's going to have unbalanced nutrition. So today, most plant physiologists that I talk to say there are 42 essential nutrients. Would any plant physiologist tell you that arsenic is an essential nutrient? No, don't have any good data. But if we're absolutely lacking arsenic, your plant's not going to grow. It's an essential nutrient at very low levels. Is arsenic an essential nutrient for you?
Yeah.
Yes, absolutely. You must have arsenic or your nerves don't function. You don't need much. What happens if we get too much? Okay, there's another problem. You know, it's the Goldilocks principle. You have to have enough, but not too much. I think, you know, given time, we're going to show that every new element in the periodic table is probably essential for plant growth. Very small quantities for some of them, but without, they don't function. So balance is a critical thing. So when these guys are eaten by those guys, all of the nutrients are going to be released in a plant available form. If your plant needs them, takes them right up. Because where are those plant available nutrients being made available? Right in the root zone. And why is it we got more bacteria and fungi right around the root zone than any place else? It's cakes and cookies. Not different than us human beings. Where do most of us spend our time? In the kitchen. At the smorgasbord. They're no different than us. So when we're looking at these interactions, these guys are going to be attracted to the root system. And now we got nutrient cycling going. Every nutrient is being released. Why would there be a release of nutrients from these guys? Because these guys contain so much more of every nutrient as compared to these predators. There's too much nitrogen, phosphorus, sulfur, magnesium, calcium, sodium, boron, everything. Too much in these guys. So these guys have to poop it out. And they poop it out as a plant available form. If your plant needs it, thank you. Now I'm going to put out the exudates to grow whatever I'm limited in. To get these guys to do the solubilization so that when these guys eat them, the plant is getting precisely the nutrients it needs in the proper balances. When we go out and we put a fertilizer on our soil, are we putting on all of the nutrients that your plant's going to require? You go put sulfur out, what are you doing to your plant? You're unbalancing the nutrients available to it. There's way too much sulfate available now, and your plant's struggling to get the other nutrients that it needs, because there's just way too much sulfur there for it to take, too much phosphorus, too much. We unbalance the nutrition of our plant. And if we're unbalancing the nutrition of our plant, this is taking up excess of something and not enough of something else. So what are you eating?
Weird stuff.
Weird stuff. Look at the unbalance of nutrients. You get way too much nitrate and not enough boron. You're getting way too much calcium and not enough zinc. So because we think we're doing right, we have messed things up but royally. And we need to put back in the natural, normal nutrient cycling system in this soil. So when you think about that, let the plant be in control of its life. It can choose what it needs to grow. What is our job in this process? Our job is to put back the full diversity, everything. All the species of the bacteria and the fungi and the protozoa and the nematodes and the microarthropods, the earthworms, everything in that picture, we need to make sure they're there. That's our job. We don't have to know that we've got species number 1, 2, 3, 4, 5, 6. How many species of bacteria are there in soil? Lots. So in working with the people at the Center for Microbial Ecology at the Michigan State University, they are showing that in a woodlot, a single woodlot in Michigan, we have well over 1 million species of bacteria. And we know that the species are different when you go into the pasture next to that woodlot. When you go into the vegetable, when you go into the riparian area or the wetlands or every single ecosystem you go into, it's a different set of species of bacteria, fungi, protozoa, nematodes, microarthropods, mycorrhizal fungi. They're all, so see, you all have to go home and practice that.
I have to say it again.
Yep, so bacteria, fungi, protozoa, nematodes, microarthropods, mycorrhizal fungi. Got that? All these guys right here. So now I've concentrated on these organisms, building structure, cycling nutrients, and of course if you get the beneficial bacteria, fungi, protozoa, nematodes, microarthropods right around those root systems, say goodbye to your diseases. There is no way that those disease-causing organisms even know that the root's there. They are protected by this massive barrier of the beneficial bacteria, fungi, protozoa, nematodes, microarthropods, mycorrhizal fungi. Now, do you need these guys? Do you need the higher level predators? Absolutely. Because what if these guys get too greedy? We would know nothing about organisms getting too greedy. So if these guys get too greedy, they're going to overeat the bacteria and fungi, and now who's going to be listening to your plant when it puts out the message saying, hey, get out there and solubilize these nutrients? Uh-oh, nobody home. Because these guys have to be present to keep those guys in line. Checks and balances. Okay, but what if you get too many of these guys? Then they'll eat these guys till they're really too low, and now all your nutrients are tied up in bacteria and fungi, and good luck, your plants are dead again. Balance, really critical. So who keeps these guys in line? Well, those guys. Who keeps these guys in line? Well, those guys. Who's at the top of the food chain? Us. Our job is to make certain they're all there. How are you going to go out and measure these organisms in your soil? How do you know if they're present? Learn how to use a microscope. And we've got microscopes. I can train you in 1 day how to use these microscopes. So where do you get the microscope? So for $350, I can show you where to go buy an excellent microscope. The objectives on that microscope are the same quality as Zeiss microscopes. And so I'll put that up on the screen here. And it comes with a camera. So if you're seeing something you have no idea what this is, you take a picture and you send it to me. And I open up the picture and I go, oh, that's an Incatreid. And you go, what? Yeah, I thought that was an Incatreid, but I just wanted to double check. So when you run into something, whoa, I've never seen this thing before, you send me the picture, and not only do I name it for you, but I explain what it does. Is it a good guy? Is it a bad guy? Should you be encouraging more? Well, what plant are you growing? Because it depends. Where in the world are you? Because that's another thing that it depends. So, that's what I'm here for, and I would love to train all of you to have this level of knowledge. So all of you will go forth and train everybody else. See, that's one of the deals here. Now that you've listened to me, you've been infected. You will go forth and explain this to other people because it's so critically important that we stop killing them and we start putting them back into our soils.